So this is joint work with Kitty Sivakrishnan and Anil Nalavdi. So once upon a time, computers could run multi-threaded programs by running each thread for a few steps and then switching to a new thread and running that for a few steps. And the result of this would be some interleaving of the steps of the threads. And this is not the case today. Everything is happening at the same time as everything else. The processor is overlapping instructions and reordering them. The different cores of the processor can see changes propagating at different rates to different processors. And even before the processor gets to touch the code, the compiler will reorder things by itself. So in order to know what a multi-threaded program is going to do, you need to appeal to the memory model of the language that you're dealing with. And this is not easy. These memory models are remarkably subtle. For instance, Nathan's example a few minutes ago involved one lock and one variable, and it's very impressive that he managed to explain its subtlety in only 20 minutes. So there's a cottage industry of papers on memory models where often the central object of study is a program 4 to 6 instructions long. So these are absurdly difficult to reason about. So how do programmers actually write programs using multiple threads in C++ or Java or whatever? So the main tool that they have available is this useful property called SC-DRF. So the idea is the programmer agrees to label every variable that's going to be used from multiple threads. They say these are going to be used concurrently from multiple threads. They say these variables are atomic variables. Or in Java, that's volatile. In C++, there's various different levels of it and so on. But the idea is that the programmer promises to annotate everything that might be used for synchronization between multiple threads and say, this is atomic. And then the compiler knows to not do too many weird optimizations when these are involved, because multiple threads might be playing with it, or to add fences to inform the hardware to take the same hands-off approach. So in return for the programmer annotating everything, the system then guarantees that the behavior of this annotated program will be as though it were just interleaved, as though the threads were running on a sequential processor one at a time. So the property of having every variable marked as atomic if it's used for multiple threads, that's known as being data race free. A data race is when two threads concurrently access the same variable and it hasn't been marked as atomic. And the property of having only the behaviors that you would see on a machine that interleaved threads is called being sequentially consistent. So hence the acronym that names this theorem, it's sequentially consistent if your program is data race free. So a shorter version of that is data race free programs have sequential semantics. And this is essentially how you try to write programs in C++ and Java. You try to ensure that your program is data race free, and then you just reason about it as though it were running on a sequential machine. But this assumption of data race freedom is a global assumption. If there's any data race on any location at any time, then this doesn't apply. So one data race in the program means all bets are off. So this is more or less par for the course for unsafe languages like C and C++, where one integer overflow anywhere in the program means all bets are off. But in safe languages, like Java, Go, Swift, or the one that we've been working on, which is OCaml, we expect the program to do something sensible. Even if there's a mistake somewhere over there, it shouldn't just cause random undefined behavior, it should cause something well specified. So the question is, what can we expect from our programming languages in the presence of data races? So one property that I think we should be able to expect, that I think is a reasonable thing, is this. If I read a variable twice, and there are no concurrent writes to the variable, then I should get the same value both times. It would be surprising to me if this fails to be true. And hopefully it'll be surprising to you when we see how it fails to be true. So the SC-DRF result is that data race-free, entirely data race-free programs have sequential semantics. What we're contributing with this paper is an extension of that. to a local data race freedom property that says the data race free parts of a program have sequential semantics, even if there are data races in the rest of the program. So we'll show, and I'll be going through them in a moment, some examples that show that this is not the case, not just in the abstract memory models, but in actual real implementations of C++ and Java. And we'll present a memory model for which this property does actually hold, as well as, which I'm not going to talk about these today, but you can read the paper, compilation schemes to XC6 and ARM, and some performance data for our implementation in OCaml that shows that these compilation schemes perform well. So first, to convince you that this is a real problem, I'm going to show some examples that I hope will be surprising. So here is a fragment of code in which we set b to be equal to a plus 10. And the assumption we're going to make is that nothing else in the entire program ever touches b or a. And I'd like to believe that after this line of code runs, b will be equal to a plus 10. But no, not in C++. Because what if the rest of the program is this? There's another variable c up there. And if you notice, the left and the right are two different threads. And if you notice on the first line, there is a data race on a different variable. It's a data race on C. Now, a smart compiler will look at the left code on the left and see, there's two occurrences of this common subexpression. A plus 10 is computed twice. That's wasted work. We should introduce a temporary so that we can cache the result of that computation and so we don't need to use it twice. So it turns it into this. There's a temporary variable t, which holds the value of a plus 10. Now suppose that computation, the ... in the middle, suppose that is quite large and complicated and needs a lot of registers. So t, this temporary, ends up having to get spilled out to the stack. A very smart compiler, when it starts noticing that things need to get spilled, will say, wait, is there some way, instead of storing this on the stack, is there some way that I could rebuild this value afterwards? Rematerialization is what this optimization is called. And in this case, it could notice that, yes, that value t is available. It's stored in C. I can read it out of there. So now, this program can quite happily produce b equals to 1, even if it's running on totally sequential hardware, just because a smart compiler was able to assume that there were no data races and got the wrong answer somehow from reading a variable because of the data race on a different variable. So we'd like a memory model which didn't do this, which protected us against data races on other variables. The data race should only affect the variables actually involved in the race. But it shouldn't just be bounded in space, limited to the variables involved. It should also be bounded in time. So here's an example about data races in the past. So supposing there are no concurrent accesses to A, B, and C while these two instructions run. So we're reading A twice, and there's no concurrent accesses to those variables. We would expect that afterwards, B and C are equal. So supposing this is in fact the program that we're running, that flag variable is anatomic, so in Java, a volatile. And we'll suppose that f is true afterwards. So there was a data race on A. But then the threads synchronized. So in this example, the synchronization is communicating via an atomic variable, but it could equally be joining on a thread or using a mutex or something similar. So we know that those two, the two writes have both completed at this point. They both happened before these two reads of the variable. So we certainly don't know whether A is going to be 1 or 2, but we'd like to think that it's going to pick one of them, that the race has ended at this point. But this is actually not the case in Java. The Java memory model allows B and C to read from two different variables, and this does actually happen in practice. There's an example at the end of our paper that has a reproduction case for it. The way it can happen is, what if there's actually two different variables, A0 and A1, and at one time they happen to alias, they happen to be the same location? The compiler spots that A0, the one read, sorry, A0, the one written to on the left, it knows that that's going to be 2, so it forwards the store and replaces the b equals A0 line with b equals 2, but it doesn't manage to do that for the second line because it doesn't know that A0 and A1 are the same thing. So C ends up reading from the other side. So after this optimization applies, we can see this outcome where b equals 2 and c equals 1. So in Java, a data race is bounded in space. We're not going to get, the previous example that I showed for C++ won't occur. We're not going to get a situation where a data race on this variable affects the results of reading from that one. But they're not bounded in time. A data race far in the past can affect things forever. What's even stranger is that data races in the future can affect things as well. And this one is particularly counterintuitive. It seems a little bit unfair for the language to give me the wrong answer because of a data race it believes I am going to do. But suppose here we have a piece of code in which we allocate a new object, a new fresh location, so nothing else in the program can possibly refer to this. And we initialize it to 42 and then we read it. We'd like to believe that we're going to get 42. Maybe there's some racy nonsense happening later, but these 3 instructions, nothing else can possibly have seen the new value. But supposing what happens afterwards is that object gets exposed via a global variable, another thread goes and reads the global variable and assigns the X field of its contents. Well, on the left, we have a load of C.X and a store to G, and those are independent. The thing that we're loading is not the thing that we're storing. And ARM hardware, at least, will happily reorder those and can sometimes execute them as though you had written that instead. And now, once it's changed to that, it's perfectly possible for A to be 7 because the thread on the right modified the value before we read it, even though this happened after. This was the code following the actual stuff that we wrote. So we would like not to have this. We would like to strengthen the SC-DRF to this local DRF property. So the tricky thing here is not actually the proof that our proposed memory model has local DRF. And that proof turns out to be about a page long. You can find it in the appendix of our paper. The tricky thing is actually describing exactly as stating local DRF. What exactly does it mean? So the intuition we're trying to capture is that all data race-free parts of programs have sequential semantics. So I'll have to quickly run through what we're describing as the semantics of the thing, of a program. We start with a machine state, which has a collection of threads and the values of all of the variables. And it performs transitions, moving from one machine state to another machine state. The transitions are reads and writes of variables and so on. And a trace is a sequence of transitions. And it starts in the initial state, which is everything initialized to 0 for simplicity. And we'll say that a trace is an SC trace if it does nothing that we couldn't observe on a totally sequential machine, where every action is a perfectly sequentially consistent one. And we'll say that an action is weak if it's something that the sequential machine couldn't do. So then we say the happens before relation relates steps when the language guarantees the order that they'll occur in. So it's a binary relation between the transitions where TI happens before TJ if they're on the same thread, and TI happens before TJ if they synchronize in the same atomic variable and the first ones are right. So with that amount of formalism, happens concurrently means that neither of them happens before the other. So that's the bare minimum of formalism to describe exactly what a data race is. So a data race is then a pair of transitions which happen concurrently, so neither of them happens before the other. They access the same non-atomic location, and they're not both reads. So that means we've got two operations, at least one of which is a write, and they're not synchronized with respect to each other. So then the SC-DRF theorem, the classical one, is if there are no data races, in any SC traces, starting from the initial state, then any state that's reachable from there is also reachable by an SC trace. So this is a lot longer than the version I presented a few slides ago, and that's because this version is actually not glossing over some important details. A particularly important detail is no data races in any SC traces. In order to determine that our program doesn't have data races, we don't need to understand all of the memory model. We only need to think about the sequentially consistent things it could do. So this is the standard statement of SC-DRF, and this is the thing that we want to generalize, that we want to describe a local version of. So the first thing we're going to do is think about data races elsewhere, data races on other variables. We want to be robust in the face of a data race occurring on a variable other than the ones that we currently care about. So we'll say that a transition, a step, is L sequential if it's either a sequential thing, a thing that the sequential machine could do, or it affects some location not in L, so where L is just some arbitrary set of locations that are the ones that we're analyzing. So then we say, instead of saying that there must be no data races at all, we say there must be no data races on locations in L. And then we guarantee that the behavior will be as though the locations in L were sequential. Next, we want to be able to talk about data races we want to be robust with respect to data races in the past. So instead of starting from the initial machine state, we want to be able to start from any machine state that doesn't have an ongoing data race. So a machine state where all of the races have happened before that state begins. And finally, instead of saying, as the standard DRF theorem says, instead of saying that the entire trace must have no data races, we want to do this step by step. We want to say there might be data races eventually, but we're going to have sequential behavior until the next data race occurs. So instead of saying if there are no data races forever, then any state that we might ever reach we could reach sequentially. We'll say, if there are no data races right now, then the next step is going to be a sequential one. And that will continue for as many steps as you want, but it means that you can reason sequentially up until the point that there's the next data race. So that means we get this local DRF theorem, which its statement is just as fiddly to express as the SC-DRF one, but it means that it handles data races on other parts of the program in a way that SC-DRF doesn't. In particular, the examples that we saw earlier are impossible under this model. So, as well as defining this new property, we've proposed an actual concrete memory model that has this property, and is also efficiently implementable, even on weak architectures like ARM. So there have been memory models that have local DRF before, even though we're introducing this new property, but it does hold to some previous ones, SC being the obvious example. But our memory model both has this property and is actually efficiently implementable. There's a major overhead in doing this is the risk that we might slow down sequential programs. That's the reason why. The assumption of no data races is in order to allow optimizations for sequential programs. So it's good to know that we have no overhead for sequential programs on the x86 architecture. And on ARMv8, a weakly ordered architecture, the overhead for sequential programs is about 0.6%. We support most compiler optimizations are still valid in this model, including common sub-expression elimination and looping variant code motion, but not all. One particular one that's not allowed is if there's a store to a variable and then a load and then another store to the variable, eliminating the first one is invalid. The main constraint that we have when compiling is that we have to preserve the ordering from loads to stores in order to prevent the data races in the future affecting current results. So that means on ARMv8, to implement this, we have to ensure that between a load and a store, there's something that ensures that order is there. And there are many things that would suffice here. A branch, or a dependent load, or the weakest form of fence. So these are all reasonably cheap to insert, but they do have a measurable cost. Conveniently, if you're writing a garbage collected language and you already have read barriers, then those will tend to include either one or two already. But still, this is the major source of measurable overhead of our approach. So here, where the overhead is still very low. So here, the blue and green bars show two different compilation schemes for our memory model, compared to compiling everything as strong release acquire, which has, so strong release acquire has up to 3.5 times slowdown on some benchmarks, and our memory model is mostly within measurement noise for overhead. There was one particular benchmark, the sequence one towards the right, where inserting our extra fences made the program slightly faster, but this is confusing, but turned out to be to do with we changed the alignment by making the code slightly longer, and we could see the speed up by inserting NOPs instead of the memory fences. So certainly the overheads of this approach seem to be like within the measurement error of our ability to tell performance of these programs. So that concludes the questions.
So thank you for a great talk. So I have actually two questions. The first one is that, so I think your motivation for localizing the DRF theorem is for modular reasoning, right? So can you explain how your local DRF fits into the big picture of modular reasoning of concurrent programs?
So the active reasoning about proving a particular program fragment correct, the reasoning looks essentially the same as when you're reasoning using the SC-DRF theorem. It's just the result that you get out of the end no longer has the globalist hypothesis. So the proof that a particular program fragment has a particular behavior looks exactly as it did before. It's just the result at the end is not if there are no data races anywhere, then it has this behavior, but if there are no data races on these variables for this region of execution, then it has this behavior.
So my second question is about the data race in the past example. So I guess that the example you're presenting violates the coherence axioms in C++ or discussed in Java memory model literature. So either A equals of T2 or A equals 1 should be ordered before in terms of coherence order. So the layer reads should read the same variable. That's my intuition. So yeah.
Yes. So if you have coherence, then this doesn't show up for the reason you're describing. Java ordinary variables don't have a coherence, like a coherence total order. There is a noticeable performance cost to introducing coherence generally, even for non-atomics, because it invalidates common subexpression elimination, which is a fairly important optimization.
Thanks for the talk. In your experiments, I was wondering, did you disable the compiler optimizations that you can't do anymore when you computed the baseline time? In particular, were you essentially measuring the overhead of inserting the extra instructions in the compilation scheme, or were you also measuring the overhead of not performing optimizations that you could otherwise perform?
So our experiments were done with OCaml, which is the language that we've implemented this model for, and the OCaml compiler, the trunk OCaml compiler does not do the redundant store elimination optimizations that are invalid in this. So we were running with all of the optimizations turned on, but yeah, these results don't directly port to, say, if we were comparing with LLVM or Hotspot, which do optimizations that would not be valid here.
I see, and I guess a related question is, do you think there would be pushback to disabling some of those optimizations if this was done for a C-like language? And also, if you did want to disable them, do you have any idea how hard it would be to work out how to disable them in the compiler, in the sense that when we give slides, it's easy to say there's this optimization, but sometimes in a compiler, things are a lot kind of nastier than that.
True. So in the context of a C-like language, what we're trying to do is improve robustness in the presence of one error somewhere in the program. The rest of the program shouldn't have undefined behavior and explode. But C fundamentally has undefined behavior and explodes when there's one variable anywhere. So I think there would be quite reasonable pushback to doing this for C to be robust to a data race when C is not robust to, say, an integer overflow somewhere or a division by 0. But I'd certainly be interested in attempting this with, say, Java, which does have safety properties in the presence of integer overflows and so on. And I suspect how much pushback there would be will depend entirely on what the overhead turns out to be in that context. Oh, cool. I'll look out for it.
Hi, Stephen. So when if I were to write a compiler optimization for C, the slogan I have in my head is that I can design that optimization under the assumption that there is no data races anywhere. Is there a weaker version of that slogan that you could offer me that works for your local DRF theorem?
I think the best version of the slogan is do whatever you want as long as you only pull loads earlier and stores later. So that actually fits a wide range of compiler optimizations, which are mostly, where a lot of them are about caching things that you have already loaded or delaying stores in case the thing might get overwritten and you wouldn't have to do the store. So as long as you're pulling loads up and stores down, then you're okay.
Thanks.
Hi. Nice talk. I might be missing something here. So you mentioned that you need to add the load store ordering constraints in your implementation. Does it mean that you need to add the constraint for all the loads or just like atomic loads?
No, for all loads, they have to be ordered before all stores.
Okay. So, okay, I see.
So that's what required the insertion of branches and so on. That was the main thing that we're benchmarking.
I see. Thanks.
Hello. Another C11, C++ question. I understand that you can absolutely blow anything up you want in C++, but saying that that means that we shouldn't give it guarantees seems to suggest that we didn't even need a memory model for it in the first place. Can you say something about what you could do for C and C++ if I give you the guarantee that the other ways we usually blow up aren't going to happen?
I mean, in a hypothetical version of C++ that didn't have, that gave well-defined behavior for all programs that the compiler accepted, then, I mean, it would be quite fun to implement this memory model, but after I'd done so, I would probably call the result Java.
Okay.
Well, thanks again for excellent talk.
Thank you.
This concludes the session.